Hey everybody, this is Larry. This is day 13th of the March Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join my Discord. Let's hang out, ask me questions. Okay, today's problem is binary trees with factors. Ooh, I just woke up, so my eyes are a little bit winky. Yeah, so I solved these live. It was a little bit slow, just fast forward and all that stuff. Okay, so binary trees with factors, what does that mean? Given an array of unique integers. Okay, we make a binary tree using these integers. Each non-leaf should be equal to the product of the values of its children. Okay. Not sure I understand what it means, but okay, let's read this again. I'll make a binary tree. Okay. Each number can be used a number of times. Each non-leaf node should be equal to the product of the values of its children. Okay. Okay, and n is about 1,000, so we can do some n squared type things, which is probably what's on my mind. The value of its children. Yeah, okay. I mean, it's a very awkward problem to phrase, but I think that should be okay. Basically, we and each number can be used to. That's a little bit awkward, but maybe maybe that's fine. Okay. Huh. So okay, so the key thing to note is that there's going to be some dynamic programming, or not even dynamic. I mean, it is you could call it dynamic programming because a lot of people call everything dynamic programming. But maybe memorization is the better word. The thing to note is that okay. The thing to note is that okay. How do I explain this? This is I actually like this problem. I think it's an interesting problem, or semi-interesting problem. So okay, so my algorithm is going to be, for kind of brute force in that. Okay, we try for each node, we try putting it here, putting a node there. I'm going to actually give me a second. I'm going to bring up. I'm going to bring up the paint thing, so then I can show you. So, oh, whoops, we got a bit too big. Hey, hang on. Okay. So basically, the thing is that okay, let's say you have 10, right? And 10 in this case have a couple of like a couple of like ways to do it, right? So it actually turns out that if you look at example 2, in this case 10 has given the 2, 4, 5, and 10, there's actually the 3 ways to do. I'm using the mouse to draw, so it's a little bit hard. I need to have 10 as the root, right? Okay. So you have something like that, right? And you could draw it out. There's 10, 2 and 5 on each side, and so forth. 10 being a leaf. But so then the question is, okay, what happens? Well, what does this mean for us for calculation, right? Well, let's say for example, now we have 20. Let's say we have the same numbers, but we add 20. What does that mean? Well, let's just say that for example, we have now we have 20 on top. You have 2 on the left and then 10 on the right? So that's one combination, but you can also think about it recursively or dynamic or memorization-y, which is that okay, this actually means the 10 actually means to get the number of trees with 20 at the root, the 10 side actually just can have 3 combinations, as we talked about before, right? So that means I'm gonna I'm not gonna write everything, but so there's 3 combos, right? So that means that now with 20 on the root, there's gonna be, you know, the 2 and the 10, and then you do the proof, you calculate, you do a count on how many the 10 has, and it's 3, so then you multiply that in. And once you kind of realize that observation, then it becomes, you know, just combinatoric, just counting stuff, and yeah, and then just a lot of multiplication to kind of get that number. I'm going to start writing the code, so hopefully that explains it a little better. I know that I hand waved this part of the explanation, but this is something that, you know, I would, if you do have trouble kind of making, you know, I think the key part about this problem is making the observation around reusing the count of a given node, or like the count of the number of subtrees for a given node. And because if you do, then the other part of the counting is just combinatorics, and or even simple combinatorics, counting, like, you know, this number of subtrees, just the number of left subtrees times the number of different subtrees that the left node can have, and times the number of subtrees the right node can have, right? Yeah, and then you could do this recursively, which we'll do together. So as I said, if this is a little confusing, don't worry, we'll look at it in code, and hopefully maybe that's a little bit easier, a little bit better. Okay, let's go. So basically we'll define a function. Let's just call this let's say num rooted tree, maybe something like that, and then we have a node, say, right? A node value or root value, maybe. Right. Let's also just set some minor stuff up as I would like to write, so that I don't have to write this later. Okay, actually now I'll convert this to a set, actually. Yeah, okay. Let's just say selection, maybe. Do I need that? I don't know. Okay, so then now we have, you know, we could set the count for this value's node, right? So count is equal to 1. We started with 1. Start with 1 because this can be a leaf terminating, right? So if this is a leaf, then you have 1 count. So that's why I start with 1. I always like to return the value, or I typed in the return value in the beginning, but that's just me. And then now, you know, we brute force on the left node, and brute force on the left node and calculate the right node, right? So okay, so now we do for left in selection. If root value mod left is equal to 0, that means, you know, yeah, then right is equal to root value divided by left, and then count, we can just add number of rooted tree of the left node times number of rooted tree on the right node, right? On the right value, that is. And of course, I'm gonna forget about the mod, so let me double. I usually do it really early, but I think because I was talking this forums, I didn't do it. So let's just do mod is equal to 10 7, and then you know, we mod it after every time. Oops. And that's pretty much it, except for that this will be exponential, as you may imagine. So yeah, but you know, this is, you know, we'll go over it real quick how to resolve that. I mean, I think I already gave enough hints, you probably would know. But yeah, so the total is you know, let's just do count is equal to 0, and then we just brute force sum up all possible roots, right? So for is this supposed to be unique? Yeah, I think so. Okay, fine. So for root in array, oh, I think I messed this up. Or I didn't mess this up. I forgot to one more check. We have to check that right is inside the selection. This is why I made it into a set. Because if right is not in selection, then we don't have to up the other number, and then we don't have to do this thing. Okay, so for root in array, or maybe even selection, just to keep it consistent, even though it doesn't matter. We sum up num-rooted tree of root, and then we make sure we mod it again, and then this should be good. I mean, it'll time out for bigger numbers, but we're going to test for correctness first before we add the optimizations. Cool, and that looks good. Yeah, so the key thing to notice is just this recurrence, where, you know, if left times right is equal to the root value, then you can't do this. The key thing to note, obviously, is that, you know, now that we kind of construct this problem in this way, we're going to call the number root tree for the same number multiple times, right? And that's kind of why we have to fix this a little bit. Because, for example, well, the examples they give you are not very good at demonstrating this. But as we said, let's copy and paste this a little bit. As we said, if we have something like, you know, let's add some numbers. Yeah, 40 is gonna call 10 times 4, and so forth, and 10 is gonna call a lot of, you know, times, right? So well, 3 times. So just so that we don't reuse this thing, we use a technique that we kind of already hinted at, which is dynamic programming or memorization. You can actually do this in dynamic programming as well, obviously, but let's see, even 6 numbers. Oh, that was actually pretty fast. I thought it would be slower. But given, you know, let me try to make this timeout real quick. I don't know. This is just random numbers, so I don't even know. But n is, notice that n is, okay, wow. This is faster than I anticipated, to be honest. I mean, n could be up to 1,000 and we're only up to 15. So let's try. I'm trying to make this time out, but why is this so fast? I didn't cache it, did I? No. Okay. I mean, this should be exponential, so I mean, I know that this kind of I don't know. I would say if I give it a submit, it would probably time out, and I'm too lazy to waste a TLE. So I'm going to tell you that I'm just going to do the memorization. Whoops. I think maybe I would maybe I'm going to do something like no, it's fine. I'm just going to do the memorization. Anyway, okay, yeah, so notice that we have repeated subproblems, if you will, which is a common part of memorization, which means that we call this function the same value, right? So then the key thing is just to add memorization. And yeah, note that for each root value, we'll do the analysis later, but let's put something in a set. Let's just call it cache is equal to a set, and if root value in cache, return cache root value, cache of root value is equal to count, and that's pretty much it. I'm surprised that this is actually went so fast, and actually technically went a little bit slower, but that's fine. Let's give it a submit. Cool. So what is the complexity of this, right? Well, It's going to be n square, because okay, we look at what are all the possible inputs to this, right? Well, there's n possible inputs to this function, because each input in R array can because each possible input has to be in array, right? So there are only let's say O of n possible inputs, and then each core does O of n work, and the O of n work is because of this for loop, right? So that means that total is O of n inputs times O of n work, which means O of n square time complexity. For space complexity, it's just going to be O of n, because as we said, there's only O of n possible input, so it's going to be O of n, right? I mean, that's the way. I mean, I don't think there's anything complicated in this part, hopefully. If so, then maybe practice a little bit on dynamic memorization. And you can also write this bottoms up. You can write this bottoms up, but I don't think yeah, I guess if you do this bottoms up, you can actually get this down to O of one space, but you can write this bottoms up with 2 pointers. But it's a little bit annoying, but definitely practice it if you're trying to really master dynamic programming, because I think that's I mean, it's going to look roughly the same, but yeah, yeah, but if you do it in a clever way, can you do no one space? No, I don't. I guess not. But yeah. So it'll still be O of n space, but that way practice practice the dynamic programming, and yeah, let me know what you think, or bottoms up dynamic programming. Let me know what you think. That's all I have. Hit the like button, hit the subscribe button, join me in Discord, and hope y'all have a great weekend. Hope you had a great week. Hope you have a great weekend. Yeah, to good health, to good mental health. Stay good, stay well, and I'll see you later. Bye bye.